This is part 5 of lecture 8 of Elect 5300. In this part we'll be looking at another example of Bayesian estimation, in particular the Bayesian estimation of the mean of a Gaussian with known variance. So let's assume the data can be described by a univariate Gaussian with unknown mean but known standard deviation sigma. So again, like the previous MLE example, we're going to assume that the Gaussian is just some kind of hill. The shape of the hill is always the same. The only thing that's different is that the mean shifts. So we need to describe the uncertainty, the initial uncertainty in the mean mu for Bayesian estimation. And we'd like to do that with the conjugate prior, and it turns out that the conjugate prior for mu is also a Gaussian, and we'll see that in the following. So the initial distribution of mu is described by a Gaussian with a mean mu0. So this is our initial guess of what the mean is, right? But we're uncertain about that guess by an amount sigma 0 squared. So we can kind of express the idea that we have almost no idea about the mean mu just by trying to set sigma 0 squared, very close, very large. So to find the posterior over mu, what we do is we multiply the prior over mu times the likelihood. We have to divide by the probability of d, but again, we don't really care about that because we're only interested in mu. So we're just going to say, well, this is not exactly equal to this, but it's just proportional to that. So the probability density function over mu, the prior probability, is just a Gaussian with this mean and this standard deviation, or variance. And the probability of the data is just the Gaussian evaluated the data and the mean mu and variance sigma squared. Now when we combine all of this information in the multiplication, we really only have to worry about the terms that contain mu. So we don't have to worry about this, and we don't have to worry about this, especially because they enter multiplicatively, so they don't really change the fact that there's a constant of proportionality there. We're going to exploit the fact that e to the a times e to the b is equal to e to the a plus b, to first take the product of all these exponentials and express it as the exponential of the sum. Right, so I get exponential of the sum of all of these guys together, which is minus 1/2 times the sum. And then I have another exponential here, which is multiplied, so I also add whatever was inside here. So minus 1/2 times mu minus mu0 divided by sigma 0 quantity squared. Now when I expand this thing out, also because of the fact that I'm only interested in constants of proportionality that contain mu, I don't have to worry about any of the terms, let's say, that contain xk squared or mu0 squared. So I really only care about the mu squared and the linear terms in mu. So when I multiply this one out, I get a minus 1/2. I just copy that from there. And then I get a plus mu squared divided by sigma squared. So I get mu squared divided by sigma squared, and then because I sum over n of them, but they don't depend on k, I get n of them. So I get n mu squared divided by sigma squares. And then here, when I multiply this one out, I get a mu squared divided by sigma 0 squared, which is shown here. And then for the linear terms, I get minus 2 times this times this. So I get minus 2 times xk times mu divided by sigma squared. And then I have to sum all of those over k from 1 to n. And then when I multiply this one out, I get a minus 2 times mu 0, divided by sigma 0 squared. So there's additional terms here in xk squared and mu0 squared, but like I said, I don't really have to worry about those because I'm only interested in the terms that contain mu. So that considerably simplifies the math. And now I'm just going to copy this to the next page, and it shows up right here. This is from page 30. Now if I look at this, mu here is the posterior distribution over mu is proportional to an exponential to the evaluated at a quadratic in mu. Right? So this has got to be a Gaussian in mu. And so I know that, well, the general form of a Gaussian is something like this, right? Except for the fact that now the mu has to take into account, the mean and the variance have to take into account that I have n pieces of data d. So I'm going to take mu n here to be the mean after I've taken into account the data here, and sigma n to be the standard deviation after I've taken in the n piece of data. So now what I can do is I can say, well, I'm again only interested in the terms that contain mu, so I don't care about this. I'm going to change this exact expression into a proportionality, and I'm going to expand this one out. And again, I'm only interested in the terms that contain mu. So I get a minus 1/2 times mu squared divided by sigma n squared, mu squared divided by sigma n squared here, minus 2 times mu n divided by sigma n squared, minus 2 times mu n times mu divided by sigma n squared. So I know that this is true from the previous page. This is true because I know that it's got to be given by a Gaussian distribution with this mean and this standard deviation. And so now, in order to figure out what this mean and this standard deviation is, I'm just going to match terms. So I'm going to say, well, the coefficient of the mu squared have to be equal to each other. So I get 1 over sigma n squared is equal to whatever was here, n divided by sigma squared plus 1 over sigma 0 squared. And I have to match the coefficients of the mu as well, so this one here has to match with that one, and that gives me this equation here. Mu n divided by sigma n squared is equal to this thing here. In order to get this, what I'm going to do is I'm going to rewrite this one as n divided by sigma squared 1 over n times sigma, it's the summation of k is equal to 1 to n of xk. Right, so all I've done is multiplied and divided by n, but then this thing here is the sample mean of the n pieces of data. So I'm going to call this mu n hat for the sample mean. So this term here is just n divided by sigma squared times mu n hat, where mu n hat is given by this thing here. It's the same thing that I derived up there, plus this thing here, mu 0 divided by sigma 0 squared. So now I have two equations in two unknowns, and the two unknowns are sigma n squared and mu n squared. So let's take these two equations over to the next page. And what I've done here is I've just simply separated out the sigma n squared. Right? So you can see here the sigma n squared was already calculated out here, and this one here was also already calculated out here. So the mu n and sigma n are copied from there, and then what I'm going to do is I'm just going to take these equations and try to solve for sigma n squared and mu n. And it's easiest here to solve for sigma n squared first. Right, so in order to solve for sigma n squared first, what I'm going to do is I'm just going to combine these two together. Right? So I get 1 over sigma n squared is equal to n times sigma 0 squared, right, plus sigma squared divided by sigma squared times sigma 0 squared. Right, so I've just combined these two coefficients together. And so when I take the reciprocal of this, I get sigma n squared is equal to sigma squared, sigma 0 squared divided by n sigma 0 squared plus sigma squared. Now what I can do is I can solve for mu of n just by multiplying through by sigma n squared, which I've already solved for right here. So what I get then is mu of n is equal to sigma n squared, which is this, times this. So I get n sigma divided by sigma squared times this thing here, so I get sigma 0 squared, sigma squared, n sigma 0 squared plus sigma squared. And so now this sigma squared and this sigma squared cancel out, right? And then I get a mu n hat. And so I get n sigma squared plus sigma squared, n sigma 0 squared plus sigma squared times mu n hat. Right? And then when I multiply this thing by sigma 0 squared, you can see that all I'm going to get is the mu 0 here, and this is going to cancel out this thing here, so I'll just get sigma squared divided by the denominator right here. Now once we've solved for this, we can express this, or kind of interpret this thing as follows. In fact, it's actually easier to look at this one here than this equation here. And so this one here, this equation here, I just got by solving this one here. But I think intuitively this one's a little bit easier. Right? And so the question is, well, this is the new estimate of the mean and the variance of the distribution over mu, right? So this is the estimate of mu, and this is the uncertainty, right? And so that what should happen is that the uncertainty should increase. The uncertainty should decrease, right? It's probably easier to look at it over here as 1 over the uncertainty, which is something we call the precision. Right? So if I am highly uncertain about something, then sigma squared is large, right? And 1 over that will be small. Right? So I'll have very little precision about that estimate. So the more certain I am, the lower this is and the higher the precision. Right? So the more data I collect, the more precision I should get. And so I start out from an initial precision of 1 over sigma 0 squared. This is the variance of the initial distribution of the Gaussian. And after I collect n pieces of data, my precision goes up by an amount proportional to n, and also proportional to sigma squared, where sigma squared is the distribution of the Gaussian variables. Right? So if the Gaussian variables have very small variance, then most of them are going to be close to the mean, and so I should be getting a lot of information about what the mean is. If sigma squared is very large, then most of them are scattered all over the place, and I don't really get that much. So the precision here increases with the amount of data I get, but also depends on how scattered that data is going to be about the mean. This one down here is just the solution of this, but we can also see the same thing here. The variance here should get smaller, and it gets smaller kind of as 1 over n, although there's this additional term over here. The mean of mu, remember my initial estimate was mu 0, right? If I took the sample mean, that would be the maximum likelihood estimate. That would be mu n hat. And so what's the actual Bayesian estimate of the mean? The Bayesian of the estimate of the mean is somewhere between the prior estimate and the maximum likelihood estimate. And what does it depend on? It depends on how much data I get. Right? So the more data I get, as n goes to infinity, this thing comes closer and closer to 1, and I'm basically going to get the maximum likelihood estimate. But for small amounts of data, this thing is relatively small, well, perhaps in comparison to this, and so my estimate is going to be closer to the maximum likelihood, the prior estimate. And so it's going to be in between those two, and you can verify that by adding this coefficient here with this coefficient here, you can see that they sum to 1. Right? So really what I'm doing is just mixing these two by an amount that depends on how much data I have. So that is the distribution then that describes the uncertainty in the mean. Right? And so we see that the uncertainty in the mean decreases, and the mean estimate is somewhere between the prior estimate and the maximum likelihood estimate. This is only an intermediate step, though. Finally, what we're interested in is the distribution over the random variable x. So we can compute that using the total probability theorem. The variable here, mu, is unknown, but we have a probability distribution over mu that we just derived, and so I can find the probability distribution over x that's implied by this distribution over mu just by multiplying these two things together and integrating over all values of mu. Now when I substitute in the form of these distributions, they're both Gaussians. This is a Gaussian with mean mu and variance sigma squared, and this is a Gaussian with mean mu sub n and variance sigma sub n squared, which are the two quantities we derived back here. And if I was going to do this in a straightforward way, I would just try to multiply these two things together and just try to do the integral and try to come up with some kind of thing that's going to give me the probability distribution over x. In fact, when you're dealing with Gaussian distributions, you should never integrate, because the integrals are very, very difficult to compute. What you should do instead is try to manipulate them so that the integrals come into a form that you know either integrates to 1 or integrates to a constant or something like that. And so we'll see on the next page that by doing these kinds of manipulations, mainly manipulating the quadratic inside these exponentials, we can get that this integral here can be split into two parts. One part here that depends only on x and mu sub n, sigma sub n. So these are all things that we estimated or we know. And this all resides outside the integral. The integral here is over mu, and so the mu dependency sits inside here. But the problem, though, is that you can see also inside this integral there's some x and some mu sub n's here. And so if this is going to be a distribution over x, then you don't really want to have it inside the integral. But if you look actually at the form of this integral here, you see that it is just an exponential of minus mu minus something squared. Right? So this is exactly a hill in mu, right? An exponential hill in mu, where the center of the hill is determined by x and mu sub n. But the center of the hill doesn't really matter because I'm integrating over this thing from minus infinity to infinity. So the position of the hill doesn't matter. So this is actually the value of this does not depend on x and mu sub n. It really only depends on the width of the hill, right? Which is determined by this parameter here, which is kind of like playing the role of 1 over the variance. And so when I compute this integral, in fact what I'll get is something proportional to the square root of this. Just like when I compute the integral here, I have to correct by the square root of the variance in order to make sure that everything integrates to 1. So when I integrate this thing here, I'm going to get something which is proportional to the square root of 1 over this. And when I do that, I combine it with this scaling factor over here. You can see that I get a square root of 2 pi canceling one of the square roots of 2 pi here, so I get a square root of 2 pi here, and then the denominator here cancels with the numerator here, and so I'm just left with the denominator down here. And then if I look at this thing here, this is simply the distribution of a Gaussian, right? So shouldn't be surprising to you that since x is Gaussian distributed, the only thing I don't know is the mean, that once I have the data, I'll still get a Gaussian distribution over x, right? And the mean of that distribution will be the estimated mean that I had before. And what's kind of surprising in this case is that the variance of that distribution is not sigma squared, right? Because in our assumption, actually, we assume that x is normally distributed with a known variance sigma squared, right? But the posterior distribution actually does not have variance sigma squared. It actually has variance sigma squared plus sigma sub n squared. And so this is reflecting the fact that actually, given the data, the distribution over x is actually more spread out than the known distribution, because there's essentially some uncertainty in mu. Because I have some uncertainty in mu, which is given by this, I have to add that to the variance to get the distribution over the x's. So there's that additional uncertainty increasing the variance above the known variance of x. And so now what I'd like to be able to do is just show you that you can do this kind of manipulation without ever evaluating the integral. So we're going to take this thing inside the integral here, and we're going to try to manipulate this so that we eventually get this equation right here. And so the derivation is shown here. I've just taken this thing here is that first equation that I had from the previous page. Now here I have e to the a times e to the b, right? So I know that's equal to e to the a plus b. So I can take these two terms outside the integral, right? That gives me this. And then I combine these two things together, so I e to the minus 1/2 times this plus this. So those are those two things combined. And now what I'm going to do is I'm just going to do a little trick. I'm going to add and subtract the same thing inside this exponential here. So you can see I'm going to add this thing here, and I'm going to subtract it out. So I really haven't changed anything, because this thing here is the same thing as that, and this thing here is the same thing as that. Okay, so really I've just added and subtracted the same thing. But now what I can do is I can pull out this portion here, because this one doesn't depend on mu. So I can pull that part out over here, and now I'm left with the integral of whatever's left over. So the integral of e to the x minus mu divided by sigma squared, this one here, and then this one here. Okay. Now, I'm still not done yet, because I have to get this into the form of mu minus something, right? And the problem here is I have a mu here and I have a mu over here. So I have to somehow combine these two together. But really now, the focus really just becomes what's happening inside this exponential. And so I can show that this one goes to this value here on the next page. So what I will do is take this term here and copy it over to the next page, just that term in the red box. So that's what shows up over here. And the first step I'll do is I will factor out this term from each of these other terms. And so the easiest way to verify that this is correct is just to re-multiply it through. For example, in this first term here, when I multiply this, the numerator here cancels the denominator here, the sigma n cancels with the sigma n here, and I'm just left with the sigma squared here, which is what I had originally. So you can verify that for this line here. Now what I'm going to do is something very similar to what I did on the previous page. I'm going to subtract a mu and add it back in. So not changing anything, but the big advantage of doing that is now I have a term here which looks like this term here, and a term here which looks like this term here. And so I'm going to group those two terms together and just expand the quadratic here. So I get x minus the x minus mu squared minus 2 times this plus mu minus mu n squared. Now what I can do is I can combine terms. So when I combine terms, I want to combine the coefficient of this x minus mu squared with this coefficient here. And so when I do that, just do it quickly here, sigma n squared divided by sigma squared plus sigma n squared minus sigma squared sigma n squared plus sigma n squared quantity squared. So to combine these two, I need to multiply on the top and the denominator, top and the bottom, by sigma squared plus sigma n squared. And now you can see I can combine the numerators now, but this sigma n squared times sigma squared will cancel with this one, and so the only thing I'll be left with is a sigma to the n, sigma sub n to the fourth, divided by sigma squared plus sigma n squared quantity squared. So that's exactly this. And you can do the same thing here. You can combine this term here with that term there to get this, and you can just multiply through by this through here to get the minus 2 times this and this. Now what I can do is I can notice that this whole thing here is a perfect square. So it factors into the square of the square root of this plus the square root of that, and then you can verify that this times this is the term in the middle, or 2 times that. And then what I can do is I can look and combine the terms here in mu and mu here. And so I'm going to get a minus this minus this, and when I do that I'm just going to get a minus 1, right, because I'm going to get exactly the same thing on the numerator as I do on the denominator, so I get a minus mu, and then I just multiply through by x on this one, add it here, and multiply through by mu sub n here, and the minus minus cancels to get a plus on this one here. And then I can just combine these two together, and because it's a square, it doesn't matter whether I take minus mu or the mu minus this, it doesn't make any difference. And I finally get this term here, which is exactly what I had then on the previous page right here. And so now this expression here is exactly the same as this expression, which is what I had on this point here. So again, I didn't really have to do any kind of explicit integration except for this one here, but I already knew what this would integrate to because basically this is the integral of something like a Gaussian distribution. Finally, I'd just like to mention what the extension is for multidimensional Gaussians. Here I'm going to assume that I have a multidimensional Gaussian but with an unknown mean vector, but a known covariance matrix sigma. And the initial mean vector, the prior distribution over the mean vector, is Gaussian with mean mu 0 and covariance a big sigma 0. And so this is the result that we got in the univariate case. We got that the mean of the posterior distribution is just a mix between the prior mean, right, mu 0, and the maximum likelihood estimate. And this mixing coefficients here should sum to 1. And that the standard deviation, or the variance of this distribution is just given by this term here. Now in the multivariate case, I get almost exactly the same thing here. If I look at this, this is the prior distribution, right, from here. This is the same thing as the MLE estimate. Or the sample mean. And here you can see I get a sigma squared divided by n times sigma 0 squared plus sigma squared. Right, so sigma squared is playing the role of the covariance matrix in this case here. And so what I can do is I get a covariance matrix, and I cannot divide in the matrix when I'm dealing with matrices. What I have to do is, instead of dividing, I have to take the inverse. But if you look at this inverse here, what you can see is that if I let's say put this n inside the inverse, I would get n times sigma 0 plus sigma, which is the same thing here. And this one here is almost the same thing here. It's just that I've multiplied this one by n. And I have, instead of here sigma, I have sigma sub 0. Comparing this one here, you see I have something very similar as previously. I have this sigma 0 over here, which is taking this one, and this one here, which is taking this one, and the division here is just the matrix inverse inside there. And by drawing analogies with the scalar case as well, if I'm interested in the posterior distribution over x, I know that that's given by the mean mu n of the distribution over mu, which is this mixture between the prior and the MLE estimate, and the covariance is given by sigma plus this sigma n, just like we had on the previous scalar case. Okay, so that's it, and we will move on in the next section to look at trying to estimate the mean and the variance.